Hello, and welcome to Lab 3, Introduction to Bathymetry and Isostasy. Consider the following observations. Massive metal ships float, submarines are able to change depth, yet small rocks quickly sink, while 90% of an iceberg may hide beneath the ocean surface. As we begin to explore the lithospheric crust floating upon the asthenosphere, we will look at why the continental crust of mountains are able to maintain high elevations, while oceanic crust lies beneath the surface of the oceans. Both of these observations reflect what's known as Archimedes' principle. Archimedes' principle. Archimedes was a Greek scientist who was given the task to determine whether the king's crown was made of pure gold. After considerable thought, he decided to take a bath. When he jumped into the bathtub, he noticed that water flowed over the edges of the tub, displaced by his mass. He jumped from the tub and yelled, "Eureka, I have it," a phrase attributed to Archimedes since his discovery. So Archimedes tested his hypothesis. First, he confirmed that the weight of the crown equaled the weight of the gold given to the goldsmith. However, when he submerged the crown in water, the crown displaced more water than the gold, proving that the crown was not made of pure gold. Thus, Archimedes' principle states that a floating object displaces a volume of fluid equal to the mass of the object. To illustrate Archimedes' principle, let's take a look at a simple rectangular boat that is 10 meters long, 2 meters wide, with a hull extending 2 meters below the ocean surface. Using these three dimensions, we can calculate the volume of seawater displaced by the boat using the formula for a rectangular solid, where volume equals the length times width times height. Thus, the volume of water displaced by the boat is 40 cubic meters. Next, assuming a seawater density of approximately 1,025 kilograms per cubic meter, we can use the density formula to calculate the mass of the displaced water, where density equals the mass per unit volume. However, to calculate mass, we must first algebraically rearrange the formula to mass. If we multiply both sides by volume, then we end up with mass equals volume times density. Thus, when we multiply the volume times the density and cross-cancel cubic meters, we end up with approximately 41,000 kilograms, the mass of seawater displaced by the boat. Archimedes' principle states that the mass of displaced seawater would equal the mass of the boat, and it does. In the previous example, the boat was in a state of equilibrium, or a stable or balanced state. Let's explore a more dynamic example of Archimedes' principle by looking at the forces involved. Here we see a floatable weight hanging from a scale above a beaker of water that has an overflow spout which flows into a graduated cylinder. With this experiment, we will take a look at the forces of gravity and buoyancy. If the weight simply hangs above the water, then the full force of gravity pulls down on the weight and it's measured on the scale. But as the weight is partially lowered into the water, the buoyant forces push upward against the floatable weight, and this creates an overflow into the graduated cylinder, but does not represent the mass of the object because a portion of the weight of the mass is offset by the hanging scale. However, if the floatable weight is lowered to where it reaches a state of equilibrium, then the gravitational force downward and the water's buoyant force upward are equal. When a state of equilibrium is reached, the floatable weight will be displacing a volume of water equal to its mass, as seen in the graduated cylinder. Again, Archimedes' principle. How high or low does a boat float? Well, it depends on the density of the boat and the density of the seawater. Recall that density is the amount of mass per unit volume, and it's reported in grams per cubic centimeter or kilograms per cubic meter. To illustrate the role of density, imagine a ship in a state of equilibrium. As cargo is loaded onto the ship, lower density air is displaced from the hull, thereby increasing the average density. This increase in density would rebalance the downward gravitational force and upward buoyant force, causing the boat's hull to sink lower into a new state of equilibrium. Mathematically, we can use the density formula to prove this point. For example, if we increase mass, then the density must increase. Conversely, when mass is decreased, then density must decrease. Isostasy. An extension of Archimedes' principle is the concept of isostasy, which is derived from Greek meaning same standing. Isostasy is the equilibrium that exists between parts of the Earth's crust, which behave like floating blocks or columns, rising if material is removed and sinking if material is deposited. Let's look at how isostasy works, returning to our ship example. If you measure the hydrostatic pressure, which is the combination of gravitational and buoyancy forces, at the sea floor directly beneath the boat, then it would equal the total hydrostatic pressure created by the boat plus the seawater. However, these two columnar pressures would be equal and they're in hydrostatic equilibrium. However, if you then measure the hydrostatic pressure at the seafloor next to the boat, it would equal the pressure created only by the seawater. Both of these measurements would be equal and are again in what's called a state of isostatic equilibrium. Any change in this equilibrium would be instantly compensated for by some redistribution of seawater between the two columns. For example, refueling the boat at sea would increase its density, causing the boat to float lower. And it would result in an increase in relative hydrostatic pressure measured on the seafloor under the boat. However, this change in pressure would spontaneously cause water to flow from higher to lower pressure until the pressure of the seafloor is again equal. In this lab assignment, you'll use these concepts of Archimedes' principle and isostasy as it relates to isostatic equilibrium. The same principles that relate to stable floating blocks of different sizes and densities directly relates to how the Earth's uppermost lithospheric crust maintains stability as it floats upon the asthenosphere. We will explore the two basic types of crust, oceanic and continental, and how they relate to global elevations on our planet. We will see that oceanic crust is typically slightly denser and often much thinner than continental crust. These differences in density cause oceanic crust to float lower in elevation than continental crust. Each type of crust is stabilized in isostatic equilibrium. This concludes Lab 3, Introduction to Bathymetry and Isostasy. It's now time to begin your lab assignment. To assist you, a separate video tutorial is provided for each section. Begin with Video 2, Part A, Oceanic and Continental Crustal Densities. Please address your questions to your lab TA.